A couple of you. Let's see. I'm just gonna have to pick a couple of people if they don't mind. Let's see. Jessica, would you have your mic on so we can participate? And Violetta and I don't know. David Thompson, would you do it? Great. And Lauren Lazarus, if you're okay with that. So everybody is welcome.
I'm sorry, what we are doing?
Just we want to make sure that Andres can actually hear people reacting to his talk. So if you're okay with leaving your mic on, that would be great.
Okay.
Excellent. Okay, please join me in welcoming Andrés Vindas Meléndez to today's session. He's going to talk about counting lattice points in polytopes. Andrés is an NSF graduate research fellow and at the University of Kentucky. He works with Ben Braun. He has some connections to University of San Francisco for his master's, or sorry, San Francisco State. Did I get that right? Sorry. And I think he's going to tell us a little bit more about the people that he knows and loves as part of his intro. So I think that'll be a great start. So take it away, Andrés.
Yeah, thanks for coming, everybody. This is great. It's kind of interesting. Now that everything's online, I get more people to come to my talks. So I'm not but let me share my screen with you all. Can you all see that now?
Yep. Yes.
Great. Okay. Yeah, so I'm going to be talking about counting lattice points in polytopes, and the title should also have been like colon an invitation to Ehrhart theory, and so I'll be telling you a little bit about that in just a bit. How do I get this to change? Great. So do you all see this ID if I move this thing, or does this cover, or is that just on my screen?
You can see it.
Okay, so I'm gonna try to move this out of the way. Okay.
Oh, well, we see your mouse, but I don't think we see like the overlay, which has, if you're like moving a.
Oh, I see. Okay, great.
All we see is your mouse.
Perfect. All right. And so on the chat, people can raise their hands in chat, right? Is that true?
If you click participants, and for me, I have to click more. There's some buttons where you can say some things, where you can like.
Yes. Oh, I see everybody. Okay, now they're raising their hands and stuff. Great.
Yeah.
Everybody should be raising hands. Okay, good. All right. Showing, raising your hands on the thing. If maybe who knows about polytopes? Or knows what a polytope is, has seen a polytope. Okay, a few here, a few there, but not everybody. So that's great. That means that I get to talk a little bit more about what polytopes actually are. So what are my main characters? My main characters are polytopes in this story. And so I'm actually, I'm pretty sure that most of you have seen a polytope at some point in your life. And so a polytope in 2 dimensions are polygons. And so we all have seen squares and triangles and things like that. So I'm almost like, now if I say, who's seen a polytope? I think everybody's hand should go up, right? And so, and in 3 dimensions, we have these polyhedra. And so the Greeks, about 2 millennia, 2000 something years ago, really people claim are the ones who started the study of polytopes. And so here we have the Platonic solids, which many of you are probably familiar with. But what is a polytope? And so if you have a solution set for a linear system of inequalities, and if it's bounded, we call this solution set a polytope. Alternatively, if we have the convex hull of finitely many points in D space, that is also a polytope. So people like to describe it, if you take just points in 3 space and you throw it up in the air and then you saran wrap them, you should be getting some shape with flat sides, and that is a polytope in 3 dimensions. And so that's what the convex hull is. So I know that Kate put on Twitter that about this question about circles and stuff, but I'm gonna let Kate down a little bit because we're gonna just be talking about convex things. A circle is convex, but things with flat sides, right? Because it has to, things that are defined by linear systems of inequalities.
So I can't have a round side.
You can't have a round side. Yeah.
Yeah, okay, whatever.
So that's let down for Kate, number 1, but hopefully everybody else cares about convex things. And so from now on, I should have put convex polytopes, because you can have polytopes that are not convex, but we're just going to focus on convex polytopes. Okay? So everybody okay with these 2 definitions of the polytopes? Maybe nod your heads if I'm.
So does bounded mean it has to be closed, or like I'm thinking like when I see convex hull of a finite set of points, I think Newton polygons, but those are not closed sets.
Right. So they have to be closed, and so yeah. So these are bounded, and so if let's just, you can see my cursor, right? So if let's consider this square or this cube, right? So you have one hyperplane. So you have actually 6 defining hyperplanes. You have like this, and everything is chopping up. So whatever's inside is bounded. So actually, if you just look at the square in 2 dimensions, you have this line, this line, this line, this line, and what's bounded is, sorry, I just pointed at my screen, acting like you could see me pointing. That shows that I do not know how Zoom works. So these things are bounded. So yeah, but that was a good question, Michelle. So why care about polytopes? And so I think everybody should care about polytopes, but maybe you need some convincing as to why you actually have to care about them. And so first and foremost, they're cool. They're very cool things to study. And so I had students, I taught this middle school and high school course on polytopes at Caltech one summer. And these kids came up with like, oh, that's so polydope. And so I use that from now on. This is, polytopes are polydope, you know? So you should be caring about this. Thank you for whoever turned on their mic. Yes,
I love a good pun. This is great. This is right up my alley.
But linear systems are everywhere. So when you have a linear system, there might be an underlying polytope. And so we can phrase questions to questions on linear systems, maybe like coming from operations research and things like this, to questions about polytopes. Polytopes are seemingly basic objects. We have all seen polytopes now, but actually determining the volumes of these shapes, these figures, is quite difficult. So that means that there's many open problems for people to get involved in research. And so many discrete problems in various mathematical areas are linear problems. So they're, or are thinking about linear systems. So there's, they're thinking about discrete volumes of polytopes, maybe in disguise. And so I borrowed some of this list from Matt Beck, who was my master's thesis advisor. But now let's talk about volume, because I'm kind of cheating you here. We said counting lattice points, but I've been talking about volume. And so counting is something very discrete, where many of us think of volume as something very continuous. And so continuous versus discrete volume. And so here I have, again, our friend, the cube. And so you can think about volume in the sense that we all know for this figure here. But what is discrete volume? And so I'm going to say discrete volume is lattice point counts. Okay? So the discrete volume of a polytope can be described intuitively as the number of grid points that lie in P. So I'm placing my polytope on my grid or my lattice z to the 3, so like z3 in this case. Okay. And so then we have continuous volume, which you might think of that, what we think of volume in everyday life. And you can think about taking the integral of this polytope, right? And so you can get continuous volume from discrete volume by taking the limit of this. And so here, I didn't say number of lattice points here, where my cursor is, this is what I'm calling my counting function. And so if I take the limit of my counting function over t to the d, I should recover my Euclidean volume. Okay, so maybe that doesn't make sense to you, but maybe we could do a little example. And so here I have a very nice triangle, and I say very nice because I did that on TixZ, and I'm pretty proud. It's very hard to do things on TixZ.
You still need to teach me.
Yeah, well, I gotta learn first. And so here we have this triangle, yeah? And so can we, well, we know how to compute the area of this triangle, right? Can somebody just tell me real quick what that area is?
1/2 base times height.
Yeah, and then this is a unit length, so this has just area 1/2, yeah?
Mm-hmm.
Great. And so the question becomes, how can I compute the continuous discretely? Is there some way where I can just use the discrete information to get back my continuous volume, or in this case, my area? And so the answer is yes. And so this is a result of Pick from 1899. So Georg Pick gave us this wonderful formula. So if you have a lattice polygon, and you have I interior points, B boundary points, then you can compute the area of that polygon by using this formula. Yeah. So a show of hands using the chat, maybe who's seen Pick's formula before? Or you could also just raise the hand if you have your screen on. Great. So some of you have seen it, some of you have not seen it. That's actually,
this is a really cool thing to show for teachers, because they have those boards that you use with rubber bands. Okay, so there's like a lattice point that has, and it has at every lattice point a little thing that sticks up.
Yeah.
And then you can use rubber bands and then make all of these kind of diagrams, and it's a really cool thing to do to try and discover this type of geoboards. Thanks, Chad. That's awesome.
Geoboards.
So I once got invited to give a talk about this exact result to a class of pre-service teachers. And when I was done, everybody, including the instructor, said, yeah, but what is it good for? So now I'm hoping you'll give me the answer.
What is it good for?
No pressure, no pressure.
Well,
I know the answer is it's cool, but anyway.
who's talking actually?
That was TJ Hitchman.
Oh, I see TJ. Yeah, TJ. I'm gonna let out number 2. If you don't like this already, that's too bad. But we'll see. Maybe it has connections.
I could take it.
Yeah.
So Andres, I have a question.
Yeah.
Does this lattice have to be like the Z lattice, or does it have to be an orthogonal lattice?
So no. Well, we could actually define our lattice. So Ehrhart. So I'm going to talk about Ehrhart theory in just a little bit. But Ehrhart theory works in using any lattice. But for me, I really care about the integer lattice, Z to the D.
Okay.
Yeah. And so, yeah, so if actually we can compute, let's come back to this example. If we move things around, we can figure out that the lattice points is the area plus half of the boundary points plus 1. Okay. And so let's actually test this. So let's make sure that I'm not lying to you. We said we were all convinced that the area is 1/2, right? Okay, so we have number of interior points is 0. There's no interior points here. Half of the boundary points, well, this is, there's 3 boundary points. So 3/2. 3/2 minus 1 is 1/2. I hope I'm doing this right. So that's nice. So the question then becomes, can we generalize Pick's theorem to higher dimensions? And the answer, unfortunately, is no. And so I think John Reeve, who was an English mathematician, I believe, gave a counterexample to this. And so his counterexample is what we call the Reeve's tetrahedron. So if you have a tetrahedron with vertices 0, 0, 0, 1, 0, 0, 0, 1, 0, and 1, 1, h, where h is just a positive integer, so you can stretch this point higher as much as you want, we'll see that there's no real generalization of this. So there's no, you can't get the volume in this case from just counting lattice points, because actually this polytope contains no interior lattice points. And you can see, and so the volume here is h/6. And so so Reeve did this counterexample just for to disprove Pick's theorem in higher dimensions, I believe. And so that's kind of a letdown. And so what can we do next? Is there some way that we can still get volume by counting? And there is a way. And this is what Ehrhart's theorem tells us. Well, one of the things that Ehrhart's theorem tells us. So show of hand, who knows Ehrhart's theorem? Almost nobody, great. Okay. Yeah, so there's a few people. Okay, or maybe one person. And my advisor and others should all know. But yeah, so if you take, so now the question is, can we count lattice points in dilations of polytope? If we take our original polytope, so we had the original triangle T, and we dilate it by integral factors, can we count lattice points in that? And so can somebody see what the lattice point count should be here for each of the dilates? It's actually not so obvious. But again, I'm gonna call L sub P to be my lattice point enumerator. And now I'm counting lattice points in dilation factors T, integral dilation factors T, okay? And so I'm gonna denote L sub P, the number of lattice points, and L sub P circle to be the number of interior lattice points, okay?
The conjecture from the chat is something to do with triangular numbers.
With triangular numbers, yeah, I can't see the chat, so I don't know.
Don't worry about it.
But
I'll amplify them.
Okay, great. So let's do this one. So actually, if we see this is just Pick's theorem with a little bit of modification, and this is because this is a two-dimensional figure, so we should be seeing some connection to Pick's theorem. Okay, and so those are the lattice point enumerators for the lattice point count and the lattice point count for the interior. And so what does Ehrhart's theorem actually say? So if we have a lattice polytope P, and we so we have a lattice polytope P, these lattice point counts are actually counted or are actually polynomial. And so it's not very obvious why that is, but the magic or the beauty of Ehrhart's theorem is that actually these end up being polynomials. And they're polynomials in T of degree D.
Mm.
Okay. And so, and we call this the Ehrhart polynomial. So if you have some background in combinatorics, and some people love generating functions, some people don't like generating functions, but if you encode the Ehrhart polynomial in a generating function, we call this the Ehrhart series. Okay? And so a corollary of Ehrhart's theorem is that the Ehrhart series is a rational function of this form. And we call the numerator of the Ehrhart series the H star polynomial. Okay, so now we have equivalent descriptions of the Ehrhart polynomial. We have this here, which we said earlier. And because the generating function is just a change of basis, we can now rewrite the Ehrhart polynomial with this polynomial basis. And we have that the coefficients are popping up are the coefficients of the H star polynomial from our Ehrhart series. Okay, so that's pretty neat, and I'll come back to that in just a second. But what do we know about the coefficients of this Ehrhart polynomial? So what is known? So we know, or people have proven, that the leading coefficient is actually the relative volume. So this C sub D is the relative volume of our lattice polytope. And if our lattice polytope is full dimensional, that is the Euclidean volume. The second coefficient is half of the surface volume. And the constant term, this c sub 0, is always 1. Okay? And we don't well, I won't say we don't know anything, but the other coefficients can still be explored. And so there's things that people are trying to understand what are the other coefficients telling us combinatorially. So let's do an example with the unit cube. So here's the unit cube. The unit cube is the convex hull of a set of points where all these xk are either 0 or 1, okay? And so, like I said earlier, we can describe a unit cube by taking its convex hull, so it's vertex description, or it's an inequality description. And so here we have, it's a set of, the inequality description says that, well, we have all the set of points such that these inequalities are met for k1 through d. So here, let's start with just the unit square and see if we can figure this out, okay? And if you're super excited to lattice point count, you can also raise your hand and BK can call you and you can choose. But the first dilate, right, so just P, has 4 lattice points. If we dilate it by 2, it should have how many? Well, 1 is 4, 2 is 9, and as you can see from the picture, 16, and then we have 25, and we can continue dilating this till your heart is satisfied. But does anybody see what Ehrhart's theorem says? Well, the lattice point count should be a polynomial. Can anybody see what that polynomial is?
T squared.
What is it?
Oh, sorry, t plus 1 squared.
Yeah, t plus 1 squared. That's right. And so we have a square grid of size t plus 1, and so this should be t plus 1 squared. Yeah.
So Andres, it's not clear. So in all of your examples so far, the origin has been a vertex.
In all my examples, yeah, but that's not.
Is that, so that doesn't matter? These counts are irrelevant of where you're scaling from?
That's right. I can shift this polytope, and I would still, like if I'm shifting it, since these are lattice polytopes. When I say lattice polytope, I actually didn't specify. I mean that the integer, they have integer vertices.
Okay. And
later on, I'll talk about when that changes a little bit. But yeah, so I can just shift these on my lattice, and I should still be getting the same lattice point count. That was a good question. So yeah, so the question now can be asked is, what about in general D dimension? Okay, and so what is the lattice point count for general D dimension? Well, what changes now is we need to count T, or we're dilating our original unit cube by a factor of T. Yeah. And so in this inequality description, we have T plus 1 options for each x to x sub k. And so we can similarly gather that the lattice point count should be T plus 1 to the D. Okay. And so what about its Ehrhart series? I had mentioned that that is something pretty cool. So let's look at it and observe it right now. And so the Ehrhart series, I wrote some of them out. The Ehrhart series for if I have D equals to 0 is that. If I have dimension 1, it's that. Dimension 2, it's that. Dimension 3 is this. Dimension 4 is this. And you can continue again till you are satisfied. And if I have any combinatorialists in the audience, maybe you can start seeing, well, one thing that combinatorialists do is ask questions that go along like the lines of, what are these numbers counting? And so you can ask this question, are the coefficients of this H star polynomial counting anything? And maybe does anybody that doesn't already know the answer see or recognize these numbers.
I'm sorry, Andres. So the H star polynomial, that's the numerator.
That's the
Correct?
numerator, right?
Okay.
Yeah. And so if you think about it, like this is a sequence of just one number. So then this is a 1 1 1 4 1 1 11 11 1. And
I have no idea, but those 11s really freak me out.
freak you out. Well, one nice thing actually is that these things are palindromic. And this is just in this example. That's not the case all the time, but questions that arise in Ehrhart theory. So now I can say Ehrhart theory is the study of dilations in polytopes. And so lattice point counts in dilations of polytopes. So one question that we could ask is, you know, what polytopes have palindromic H star polynomials and things like this, yeah? But if you continue, and I claim that with a little bit of thought, everybody can come to the conclusion that you'll have some polynomial, right, up to dimension D, right? And so the Ehrhart series of the units cube actually looks like this. And so what
in the chat notice that the sum of the coefficients is n factorial. So that certainly seems like it could be counting a permutation of something.
Yeah, yeah. And so actually a theorem by Euler and Karlitz says that this number, so the coefficients are known as Eulerian numbers, and they equal the number of permutations of 1 through t having exactly k descents. And so what does that mean? Well, let's look at this example. The permutations of 1, 2, and 3, and their descents are these. So what are the permutations of 1, 2, and 3? Well, we have 6 which is 3 factorial, right? And so here we have 1, 2, 3. How many descents are there? Well, there's none in this case. There's 1 descent here, right? Because 3 descends to 2. There's 1 descent here because it goes 2 descends to 1. Again, 1 right here, 3 descends to 1, 3 descends to 1 here. And here we have 2 descents because 3 descends to 2 and 2 descends to 1. Yeah, everybody with me?
Mm-hmm.
Yeah, and so, and so these are actually, so the number, so here we have how many permutations with 0 descents? Well, we only have 1, which is the coefficient of C sub 0, which is 1 here. And then we have 4 with 1 descent, which is the coefficient of C sub 1, right? And then we have just 1 again in this case. Yeah.
So there's a 200-year gap in the proof of this theorem. Did something happen?
So I think it's that Euler observed it and Karlitz wrote what we consider now appropriate proofs.
Okay.
Yeah. But I might be wrong, and other people can chime in on the chat.
Euler was busy, man. He had a lot of stuff to do.
Yeah, I'll briefly say that Euler investigated these particular power series in the context. He was studying reciprocity theorems for the Riemann zeta function before the Riemann zeta function was named that, and he needed these power series, and he came up with these rational functions, and so that's why the numerators are known as Eulerian numbers. But as far as we all know, nobody made the connection to descent statistics until the 50s with Riordan's work. So these were kind of around in analytic number theory, but the combinatorial connection wasn't made for a long time.
And that's my advisor, everybody.
Hi.
Great. And so I'm going to stop here real quick because I think it's worth mentioning some history. And one thing that I like to do is we should really, well, that I really believe in my heart of hearts is that we should know the people of the math that we study, including ourselves. So we should first get to know ourselves. And the second is who we're studying. So this is Georg Pick, who was an Austrian mathematician. Does maybe with a show of hands, either with a chat or actually physically raising your hand, know about Pick? Anything about Pick?
He has a theorem?
He has a theorem. Actually has a lot of theorems. In this one, I called it Pick's theorem, but Pick's theorem can also refer to a lot of things. Actually, Georg Pick was an Austrian mathematician who was actually good friends with Albert Einstein. And so at the, I forget the name of the institution, but I'm going to say, okay, well, whatever. I forget the name of the institution, but when Albert Einstein was, well, Pick advocated for Albert Einstein to get the chair position of mathematical physics at this institution. So they were really good friends. But actually, Pick moved back to his home, I think in Vienna or something like this. And then the Nazis came into power, and he was sent to a concentration camp and later died. So that's a very sad story, but he did do a lot of beautiful mathematics. He did do a lot of beautiful mathematics. Not do well, I don't know his personal life, so.
This talk just got way racier.
So yeah, so we'll leave his personal life out of it. We'll just study his mathematical topic. But on the other side is Ehrhart. So Eugène, Kate, you said your French was bad, but it's probably better than mine. So how do you pronounce the French version of Eugene?
Eugene. You're good.
I think it's like Eugène or something like this, but
could be. My grandmother would know.
But yeah, so this is Ehrhart, and Ehrhart was a French mathematician who actually did most of his mathematical research as a high school teacher. And so he was doing great mathematics as a high school teacher, and his colleagues were like, well, you're doing, pretty neat stuff. Why don't you go and get your PhD? And so he actually went on to get his PhD at age 60. So I guess a life lesson from that, it's for the grad students that are listening, it's never too late to get our PhDs. And so we should never have a time constraint on what we actually enjoy doing. And so, yeah, so these are two little tidbits of their story, their life. So I'm going to move on to now Ehrhart Quasipolynomials. So right now I've been just talking about polynomials. And so now, instead of just taking the convex hull of integer points, I'm going to take the convex hull of rational points. And so lately I've been doing a lot of work and thinking about rational polytopes. And so Ehrhart's theorem actually generalizes to rational polytopes. And so the lattice point count, instead of being polynomials, are now what this word is, quasi-polynomials. And so I'll tell you right now what a quasi-polynomial is. But Ehrhart's theorem, if you have a rational polytope, the counting functions are actually quasi-polynomials. And a corollary is that now if you, again, put the the lattice point count into a generating function, the Ehrhart series also has a similar form, a rational function, only that now you have this Q popping up here. And again, I want to say that you don't have to write things in this denominator, but it's just nice. And so by convention, we assume that this H star, or I'm going to claim that this is the H star polynomial with this denominator in the rational function. But Q here is actually the least common multiple of the denominators of the coordinates of the vertices. Okay, and so we'll see that in an example in just a bit. But what is a quasi-polynomial? Well, quasi-polynomial is a function of this form, where now you have the Ci are periodic functions. So that's one definition. We could also look at it like this. It's a lattice point count where we have kind of different polynomials for the period. And so this Q is what I'm calling the period. Okay. And so what are some known results about Ehrhart theory of rational polytopes? Well, first, I think we should do an example. So let's take the convex hull of this figure right here. And so what is our Q? So our Q, well, I see BK point going like this. So can you all see what shape you get from this? So it's two-dimensional, so nothing too crazy. Lauren?
Oh, I was...
We're also visualizing, okay.
I think we've shifted the cube to the left.
Yeah, so this is actually this square. Yeah. So we kind of.
Yeah.
Mm-hmm.
Not cube, square.
It's not a square. Oh yes, it is. Never mind. I can't add. Sorry.
Well, yeah. Well, this is.
Well, no, it is in the square.
It's a rectangle.
It is in a square. It's a rectangle. So that's right. So yeah. So you have this.
Okay. Okay. I'm good. I can add.
Okay. Great. Yeah. Okay. So you have this rectangle, and so what is our Q? Our Q is 2, right? Because I said Q was the least common multiple of the coordinates of the denominator of the coordinates, right? And so here, everything, if I were, this is 2/2, everything should be, so I get that Q is 2. Yeah, everybody with me?
Mm-hmm.
Yep.
Okay, so then if I go back to what a quasi-polynomial looks like, it means that I should have polynomials, should have 2 polynomials, right? And so I actually do get it. And in this case, we actually only care if our dilation factors are even or odd, right? So if I dilate this by an even number, if my dilate is an even number, I get this polynomial.
Mm-hmm.
That counts my lattice points. And if t is odd, I get this. Yeah. Okay. And you can also see that when I dilate this by a factor of 2 or by an even factor, I should be getting a lattice polytope, right?
Right.
So that means that this has to look like the Ehrhart polynomial for that integral dilate.
Yeah.
I mean, for the integral polytope after I've dilated it. Yeah. And so if I give you if you see a polynomial and you don't see this 1 at the end, then you know that it's not an Ehrhart polynomial. Okay.
Mm-hmm.
So just for amusement, here is the Ehrhart series of this polytope. Okay. And also notice that this is also palindromic. And while I won't tell you why this is palindromic, I will encourage you in a couple of months to read my paper that I'm writing with Ben and Matt Beck, and that answers actually partly why this example is palindromic. But yeah, and that's a stay tuned.
Mm-hmm.
Okay. Because since I'm so good at plugging myself, I'm going to continue advertising my work. And so actually this is work that I've done. So this is the polytope, the bigger polytope is called the permutahedron. And so what is the permutahedron? If you take the convex whole of all permutations of 1 through n, then you should be getting, that's what we call the permutahedron. Here, this is the permutations of 1 through 4. And notice that this is a 3-dimensional polytope living in 4 space. Okay. And so in recent work, we studied, I didn't say who we was, myself and some other people that'll pop up here, studied these polytopes when you have a group acting on the polytope. So if I take a group element from the symmetric group and I act on this polytope, it fixes some inner polytope.
Oh.
And so this is what we call the fixed polytope of the permutahedron. And so again, like the common theme in Ehrhart theory is, can we count the lattice points? And the answer is, well, the first effort was maybe. And so work with Federico Ardila, who was one of my other master's thesis advisors at SF State, who might also be listening. So hi, Federico. You don't have to reply. You're probably busy. But so with Federico, I started this work, and Anna Schindler, who's now a community college professor at North Seattle College. And this was to answer a question posed by Alan Stapledon, who's an Australian mathematician. And so he asked to determine the equivariant Ehrhart theory. So equivariant, fancy term for thinking about things with group actions. And so if you act on the permutahedron, can you tell me the lattice point counts for the polytopes that are fixed by that action. And so our first work was maybe. It seems a little hard. And so we were able to write a nice formula for the volumes. And then in more recent work, we were able to successfully answer the question. And this was work with Federico and his PhD student, Mario, who's a PhD student at UC Berkeley. And so both of these papers are now on the archive, and they're appearing in these journals that I'm listing there. But if that interests you, you should definitely look into these papers. And I want to say that Ehrhart theory is nice in its own right in discrete geometry, but has a lot of ties in different areas of mathematics. And so in this paper, like Reverend Ehrhart theory of the polyhedron, we actually use tools from number theory and algebraic geometry to answer some questions. And so, BK, you had a question?
Well, when you're done with that thought, we have two questions from the chat.
Okay. I do want to say, okay, yeah, maybe I'll answer the questions on the chat.
So one of them is an observation that going from 2 to 3 dimensions is like what we do in Calc 2, where we sort of integrate up. And I think there was I wonder if that has anything to do with how the polynomials change as you go up in dimension. Things like, Stephen, is that fair? Does that?
Sorry, I didn't understand the question.
Stephen, do you want to ask it out loud?
So basically, I was wondering, in Calculus 2, you learned that you can take the integral of a two-dimensional graph and basically say that maybe like a rectangle and of it up, and you would be able to find the area because you would be able to take the integral from the length times width of the whole entire thing. Is that kind of similar to how you could do that with these kinds of dimensions with lattice points?
Yeah. So like I said earlier, this was a really good question. So you can determine the volume of these figures, and this is higher dimensional volume by integrating. And so actually we can avoid like double and triple integration and all that stuff. Because, so like I mentioned earlier, if we just take the limit of of our Ehrhart polynomial divided by t to the d, we should recover the volume. And so we're actually avoiding all integration, but integration is lingering under there. Hopefully that answered your question, Stephen.
Yes.
And the other question was, can you give us a polytope where the Ehrhart polynomial is not palindromic? Like, is there a horrible geometric property that guarantees that it won't be?
For an Ehrhart, so our Ehrhart, the H star polynomial.
Sorry, the H star, yes.
Yeah. So there's actually, yeah. So actually, most, I wouldn't say most, but a lot of H star polynomials are not palindromic. Actually, the question is, can we figure out polytopes that do have palindromic H star polynomials? And so actually, it was just coincidence that these ended up being palindromic, but most won't be palindromic.
Okay, thanks.
Great. And so this is a result. So I have only a couple more minutes, and so hopefully I'll be done soon. But this is a result by Ehrhart. Well, it was partly done by Ehrhart and then finished by McDonald. We call Ehrhart-McDonald reciprocity. So if we have a rational polytope, then if we substitute negative t to the lattice to the Ehrhart quasi-polynomials, we should have a count for the interior lattice points. And so this is actually really neat. And so I took this from Computing the Continuous Discretely, which is a book written by Matt Beck and Sinai Robbins. So in combinatorics, there are classes of theorems called reciprocity theorems. So if you have a counting function, because we count in positives, it makes sense to substitute integer values, right? But if you have a polynomial, then a kind of crazy question is, well, what if I substitute a negative value into it? Does that count anything? And so it's a beautiful result by Ehrhart and MacDonald that if you plug in negative t, you're actually counting the number of interior lattice points for the polytope. So I thought I would share that with you. So actually learned this from Federico, was this proof. And so
can I interrupt a sec? Does that play nicely? I guess that must play nicely with our example from a little bit ago when we were doing the even versus odd case.
Yeah. So that definitely plays a role in it. And actually, we could see in even further just the integral case when we were doing for the cube, we had that the lattice point count was t plus 1 to the d, right? But if we want to just if we just wanted the interior points, then we don't actually have a t plus 1 size grid. We have a t minus 1 size grid, right? Because we don't care about the boundary points. And so so our Ehrhart polynomial for the interior, the Ehrhart polynomial for the interior polytope, the interior of the polytope, should be t minus 1 to the d. And if you just use Ehrhart MacDonald reciprocity, if I plug in just negative t, and then multiply it by its corresponding dimension, I should be getting my results again.
Cool.
That makes sense?
Cool.
Or I said it out loud, and it's hard because I would have normally written this instead of me saying things out loud. And I want to say that to appreciate rational polytopes, I think it's very underappreciated, but I think you should appreciate it. But the difficulty that arises from rational polytopes is there's a lot of underlying number theory that goes on, as we can see coming from considering the periodicity and all these things. But now that we have tools in Ehrhart theory, let's come back to Pick's theorem. And so yeah, I was saying that I learned this from Federico. So Federico Ardila is a professor at SF State, and back in 2011, I went to a SACNAS conference, and he gave one of the keynotes there, and it was counting lattice points in polytopes. And now, almost 9 years later, this is what I end up doing. So I think it goes to show that people can have really impactful interactions. But let's go back to Pick's theorem. Pick's theorem, now we know and love. Well, maybe not somebody who was the one who complained earlier. But most of you hopefully now have an appreciation for Pick's theorem, right? But let's give a proof using Ehrhart theory. Okay, and so Kate, I also wrote Euler's polyhedral formula in my abstract.
Yeah, I saw it.
Because you stated it, I took it out. No, I'm just kidding. No, actually, it's a much simpler proof. So actually, one way to prove Pick's theorem is to triangulate the polygon and have some applications of using Euler's polyhedral formula. But I'm not giving that proof because it's kind of long. So I'll give you the shorter proof that I learned from Federico. So we have a lattice polygon. So we claim that the Ehrhart polynomial should look like this for the lattice polygon. Yeah. Using Ehrhart MacDonald reciprocity, we should have this be the lattice point count for the interior and the interior points. Everybody with me so far? Nothing crazy? If I substitute t equals 1 to my Ehrhart polynomials, right? I should be getting the number of lattice points of my original polytope, and then the number of interior lattice points of my original polytope. Yeah? So that means that now my lattice points are just c sub 2 plus c sub 1 plus c sub 0. And then my interior lattice point count is c sub 2 minus c sub 1 plus c sub 0. Yeah? No, I see a face of confusion.
Oh, I was reading a question from the chat. It was, is there any generalization to non-integer dilations? And I was trying to remember.
Actually, people
I
have
was
done,
thinking about that. Yeah.
people have done work on this. It's something that I haven't considered, but people have done work on
Yeah.
non-integral dilations.
Right.
Yeah,
But no, you're what you were saying was not confusing me.
Okay.
You're good.
but I'm glad that you're at least thinking about these things. Okay, and so yeah, so here we have that these are the number of lattice points and the number of interior lattice points. Okay, so that means that the boundary points, the number of boundary points, should be the number of lattice points minus the interior. Everybody agree? Nothing crazy there. Yeah. So then, if I were to rewrite this, I get my interior plus b over 2, right? So I get my boundary point should be, if you work it out, should be 2c sub 1. Yeah. Everybody with me? So I'm just subtracting this and this. Yeah. Rewriting everything, or I get that my interior points plus half of my boundary points, right? If I solve for b here, and then I'm just gonna do a little trick where I just add 1 and subtract 1. So I have a -1 here and a -1 here. Yeah. This should kind of look like Pick's formula. Yeah. But Ehrhart's theorem says c sub 2, right here, should be my area. And c sub 1 is always 1 for an Ehrhart polynomial. So c sub 0 is 1, sorry. And so now the result follows. So I plug in here area, c sub 0 is 1, and then I solve and I get everything nicely and looks like Pick's theorem. Yeah? So that is much shorter than having to use triangulations and then Euler's polyhedral formula. Yeah. So just to end, let me just give you a few more results. One thing that you might have noticed is that the H-star polynomial always has positive coefficients. And so this is a result by Richard Stanley from the 80s. And so he's actually the one who proved also that it's of this rational form. Okay. Now, some of you might have a question on whether Ehrhart polynomials have negative, or are they always positive coefficients? And so the answer is no, there are cases. Actually, if you take the Ehrhart polynomial of Reeves tetrahedron, you should get some negative things coming up. Another result by Stanley is his monotonicity property. So what does this say? So if you have a polytope Q, and then you have a polytope P inside of Q, the H-star polynomials dominate one another. What that means is that the corresponding coefficients for H-star of P and H-star of Q, so the coefficients of H-star of P are dominated or are bigger, or sorry, are smaller than the H-star coefficients from Q. Sorry, I don't know if I said that right, but I think you get that.
And so that's capturing, that's a generalization of like the area axiom, that if you're contained within, you have less area.
That's true, right? Because you would be able to work a little bit backwards. Actually, you can recover the volume from just the H-star polynomials. Actually, the leading coefficient of the H-star polynomial is the volume. So yeah, so what you said is right. It does follow from this. And so work that is soon to, hopefully in the next month, 2 or 3, who knows, after this pandemic, will get done eventually, is we can rewrite the H-star polynomial of a rational polytope. We can decompose it in a way that brings in arithmetic data from simplices of a triangulation. So if you triangulate a polytope, I can rewrite the H-star polynomials with information coming from a triangulation and the phase structure of that triangulation. So I didn't write anything too deep here because I didn't want to confuse your notation, but that's coming soon, hopefully. And so I'm out of time, but maybe one of you will ask me, what can I do? And so somebody please ask me about open problems so I can finish this slide.
Can you tell us about open problems?
Okay, thanks everybody. One question is actually for Ehrhart polynomials are classified for dimensions 2 and lower. What do I mean by classified is if I give you a polynomial, can you give me a polytope that has that Ehrhart polynomial? So that's actually open for dimensions 3 or higher. It's become a really challenging problem, and it's, you know, a lot of people have been thinking about this. So because there's this relationship between the H-star polynomial and the Ehrhart polynomial, we could ask the same question: can you classify all H-star polynomials? And so an open question is, can you classify H-star polynomials for rational polytopes? Can you find families of polytopes where the H-star polynomial is unimodal, right? Unimodal meaning you have a sequence that increases and decreases. Something also related is when do you have palindromicity happening? And so there's plenty of things to study. So things have been conjectured. The H-star polynomial is unimodal, has been conjectured for a whole bunch of polytopes that I've listed here. So you're welcome to start looking into those. You could also study the roots of Ehrhart quasipolynomials and Ehrhart polynomials. And maybe it might be too difficult, so you might just want to fix it for a certain dimension. You might study the roots of the Ehrhart series. So a lot of people have been doing this work. And yeah, so there are questions there. And so I'm gonna stop here. So this is Ben Braun, my PhD advisor, and this is Federico Ardila, Matt Beck. These are my master's thesis advisors. So you can credit partly part of them for my interests in Ehrhart theory. So.
All right, we can all unmute to clap, and then we'll see if we have time for a couple of questions. Great. We have we asked a lot of questions as we went, but we have about 3 minutes. So if anybody would like to ask another question, please go for it.
So I saw it in the chat earlier, somebody was asking, and I'm going to play off of it, of whether those properties about the coefficients, like being palindromic, or you were sort of adding on to that with the unimodal coefficients, what those properties might get us, or sort of what's nice about having those properties in our polynomials there.
Yeah, that's a good question. So people in algebraic geometry have, and I'm not an algebraic geometer, so I can't answer that completely, right? But hopefully by getting those properties, we can at least become a little bit closer towards like getting families of polytopes that can be classified. So like if I don't know if that makes sense, but at least that's something that I have in the back of my head. It's like, okay, if I find polytopes, if I have H-star polynomials that are like unimodal, I can try to find families of polytopes that meet that, and hopefully that can tell me, you know, there's some structure there that I can classify when this is happening. So there's some classification things that I'm interested in, but maybe that's not what everybody else is interested in.
Cool.
Yeah. Thanks, Lauren.
Anyone else? Okay, we're getting some people say they got to run, so I think we'll wrap up there one more time. Thank you, Andres, for your talk.
Yay! Thank you.
And excellent job, featured friends, engaging and helping this feel like a live conversation. I really appreciate it. This talk will go up on our YouTube channel as soon as it processes. Oh, and since next week's speaker, Jessica, is here, yes? You're next week.
Next week?
Oh, no, sorry.
No.
Many weeks from now. Who is next week?
Sandra Kingen.
Sandra,
about matroids.
Yeah, Sandra Kingen is talking about what is a matroid. And if you don't know what a matroid is, like I don't.
That's the point of next week.
That is a good question. And so, great. Thank you all.